We have seen that empty set is a relation. If you take any two sets A and B, a relation is a subset of A cross B, and empty set is a subset of every set. So empty set is also a subset of A cross B. So empty set is a relation from A to B. So empty set is a relation from any set to any set. Void relation, empty relation. Now, is it a function? It's a relation. Okay, great. Is it a function? Suppose it's not a function. A function is to satisfy two conditions. What are the conditions? First condition is that for every element of A, say for every element x of A, there should be an element y of B such that the ordered pair xy is that is one property. Second property is that for no element of x of A, there should be two distinct elements y1 and y2 of B such that xy1 is in F and xy2 is in F. So there are two properties for a relation to become a function. So if empty relation is not a function, one of these conditions are to be contradicted. Is it possible? If phi is not a function from A to B, one possibility is that there is an element of A there should be an element of A to which there is no image. Yes, suppose A is non-empty. Suppose A is non-empty. Then you can choose an element, say x of A. And this function phi takes x to no element because there is no ordered pair in phi. So this is not a function. So phi is not a function from A to B if A is not equal to the empty set. The problem is that if A is not the empty set, A will be having an element x which cannot be mapped to any element of B by the function phi because phi contains no ordered pairs. So in that case it's not a function. Now suppose A is equal to phi, what happens? Suppose A is equal to phi, that is phi is a function from phi to B. Is it possible? Yes. Phi is a subset of phi cross B. Phi cross B is a phi, so it's a function. It's a relation. Now, for every element of phi, there is an image. For every element of phi, there is an image. How will you contradict that? In order to contradict that, we will have to establish the existence of an element of phi with no L. That is impossible. Why? Because phi cannot contain. There is my claim is that for every x element of phi, there exists an element of y in B such that this is the claim I want to prove. Suppose not. My claim is that for every x in phi, this should be true. If this is not true, what happens? Then there exists an x in phi such that this condition is violated. That such that for every there does not exist a y in B such that xy belongs to B. This cannot happen because empty set cannot contain any element. So every element of phi satisfies this condition. And there is another way in which phi is not a function. That the one element, if one element of phi is mapped to two different elements of B, then also we can say that phi is not a function. Is it possible? We cannot prove that. If you want to prove that, first we will have to establish the existence of an element of phi, say x, with two images, y1 and y2, and that is also impossible. So we cannot prove that f is not a function. Therefore, f is a function. That is the advantage of this. Every statement is either true or false and not both. So in order to prove that something is true, you can prove that f is false, that statement is false is not true. Because if the statement is false is not true, then the statement is true. So you cannot prove that, you cannot disprove the statement, therefore the statement is true. But of course, this will cause some confusion for some people. Earlier I had stated that the statement P implies Q is true when P is false. Last time we checked the truth table and observed that the statement P implies Q is true, is always true when P is false, irrespective of whether Q is true or false. That is the important thing. So if X is an element of phi, if that is your P, whatever be the Q, suppose this is your P and you write some Q, whatever be Q, then this statement will be true. X is an element of phi can never be true by the definition, because empty set is a set with no elements. So this is never true. So if this is the statement P, then whatever be Q, P implies Q is true. So that is why this statement is true. So if X is an element of phi, there is a unique element of B such that X, Y is an element of phi. That statement is true. So what is the conclusion? So phi is a function from A to B if A is equal to phi. and it is not a function if A is now here is a notation. If A and B are sets, A to the power of B to the power of A is the set of all functions from A to B. The notation, if A and B are sets, B to the power of A is the set of all functions from A to B. This is a notation. There is a reason behind this notation. Suppose A and B are finite sets. Suppose that A and B are finite sets. Then how many functions will be there from A to B? Suppose that A contains m elements and B contains n elements. Then we can see that B to the power of A will contain B to the power of A will contain n to the power of m elements. That is why we prefer this notation. So we can write number of elements of B to the power of A is equal to number of elements of B to the power of number of elements of A. How will you prove this? Now, you take an element of A. You take an element of A. That can be mapped to any element of B. You take an element of A. That can be mapped to any element of B. And how many elements are there in B? There are n elements. So you can map that element of A to any one of these n elements, and that can be done in n ways. That is for one element of A. Now you take another element of A. That can be mapped to these n elements of B, any of these n elements of B, and that can be done in n ways, etc., for every element of A. So altogether, and mapping of one element will not prohibit you from mapping another element similarly, because all these things can be done independently. So what happened? So what are the total number of ways of mapping elements of A to B? That will be n into n into n. How many times? M times, that is n to the power of n. So the number of elements of B to the power of A is equal to number of elements of B to the power of number of elements of A. Note that the same thing is true even when the sets are empty, or A and B are empty also. For example, suppose A is empty. Suppose A is empty and B is non-empty. How many functions are there from A to B? Such a function from A to B will be a subset of A cross B, that is phi cross B, that is equal to phi. There is, for phi there is only one subset, phi. And we observe that when A is equal to phi, there is a function. So there will be only one function. So the cardinality of this set will be equal to 1. Now if A is non-empty and B is empty, A is non-empty and B is empty, then how many functions can be there? When A is non-empty and B is empty, A cross B is again empty set. So there is only one relation, phi, and that relation is not a function. Why? Because there is an element of A which cannot be mapped to any element of B because there is no element B. So that means there is no function from A to B in that case. So that is the cardinality of B to the power of A in that case will be equal to 0. And what if A is equal to the empty set and B is also equal to the empty set? Then what is A cross B? Empty set, and there is only one relation, and that relation is a function because A is empty. So there the cardinality of A to the B to the power of A is equal to what? 1, because there is one relation, there is one function 1. And so what is this? This is equal to cardinality of B to the power of 0. And something to the power of 0 is equal to 1. And here this is equal to here B is empty. So that is 0 to the power of cardinality of A. That is equal to 0. And here both are 0, so this is just 0 to the power of 0. So for all finite sets A and B, the number of functions from A to B is equal to cardinality of B to the power of cardinality of A, and that is why this symbol, this particular symbol B to the power of A is used. As I told you, A cross B, the cardinality of A cross B is equal to cardinality of A into cardinality of B for finite sets A and B. In the earlier we defined 0 as the empty set and 1 as a set containing only the empty set. That is, 1 is just a set containing 0. And I define 2 as a set containing 0 and 1. That is a set containing empty set and a set containing So what is 2? 2 is a set with only 2 elements. Now if A is any set A, if A is any set, what is meant by 2 to the power of A? Two to the power of A is, what is 2? Two is just 0, 1, the set containing 0 and 1. So this means the set of all functions from A to a set containing 2 elements. Such functions are special, they are called characteristic functions, and they correspond to the subsets of A. That is, let A be a set and B a subset of A. Then we can define a function chi B from A to as follows. Chi B of an element X is equal to 1 if X is an element of B, 0 if X is not an element of B. A is a set and B is a subset of, not necessarily proper subset, can be A also. Now we are defining a function. I am calling that function chi b. It's a standard notation for characteristic functions. Chi b is a function from A to the set 2 with the property. It's defined as follows. An element is given the value 1 if it is in B. An element means an element of A. This function is defined from A. So x can be any element of A. If you take an element of A, that can be either in B or in the B complement. If it is in B, we give the value 1. If it is not in B, that is in the B complement, we give the value 0. So this is a function. So this is a well-defined function. It's called the, this function is called the chi b is called the characteristic function of the subset. So for every subset B of A, we can define such a function called the characteristic function of B. Now you will look at any function from A to this set that takes value 0 at some points and takes the value 1 at some points. You take the set of all points at which it is equal to 1. That will be a subset of subset B of A, and that function will be a characteristic function of that subset. That is, if f is any element of 2 to the power of A, you define B as the set of all x element of A such that f of x is equal to 1. This B will be a subset of A, and what will be f? F will be nothing but the characteristic function of B, because f of x is equal to 1 if and only if x is an element of B, that is if and only if chi b of x is equal to 1, and f of x is equal to 0 if and only if x is not an element of B, if and only if chi b of x is equal to 0. So that means f and chi b are one the same. My point is that every characteristic function is an element of 2 to the power of A, and every element of 2 to the power of A is a characteristic function of some subset of A. We can even now, what is the set of all subsets of A? That is denoted by this symbol P of A. What is it? Power set of A. Power set of A. Set A is the set of all subsets of A. Now, can we find a function between power set of A and 2 to the power of A? A function from power set of A. What are the elements of the power set of A? Subset. So an element of power set of A will be a subset of A. Now you map that to the characteristic function of that subset. And that will be, characteristic function will be a function from A to the two elements at 0 and 1. That means it's an element of 2 to the power of A. So this will be a function from the power set of A to the set 2 to the power of A. That is, corresponding to every subset of A, there is a characteristic function, which is a function from A to the two element set. And this function is 1, 1 and 1, 2. this function from power set of A to the Cauchy functions. That is taking a set to the Cauchy function. Because this function is 1, 1 in the sense that if you take two different sets, different subsets of A, the Cauchy functions will be different. And every element of 2 to the power of A will be a Cauchy function of some subset B of. If you take B as the empty subset, this function will be 0 always. This constant function 1. And if you take the subset A of A, the Cauchy function of A will be taking the constant value 1. So that is there. And of course the other. So there is actually a 1-1 correspondence between the collection of all subsets of a set and the collection of all Cauchy functions, or the collection of all functions from A to the two element set 0 and 1. So there exists a 1-1 correspondence between power set of A and 2 to the power of A. Or there is a bijection between these. There exists a bijection. One consequence is that both of them will have the same number of elements. If there is a bijection between two finite sets, suppose that A is a finite set, that power set of A will be a finite set, 2 to the power of A will not be a finite set, and both these sets should contain the same number of elements. And what is the same number of elements? If A is a set with n elements, how many subsets will be there? If A is a set with n elements, how many subsets will be there? 2 to the power of n. And what is the cardinality of 2 to the power of A? That is equal to cardinality of 2 to the power of cardinality of A. Cardinality of 2 is just 2 elements. This is just 2. So both the sets are having the cardinality 2 to the power of cardinality of A. And there is a 1-1 correspondence between them. And for this reason, sometimes we identify these two sets. And some people use the notation 2 to the power of A for the power set of A. Some people identify the power set of A with 2 to the power of A. Then instead of writing power set of A, some people write 2 to the power of A. Strictly speaking, that is not correct, because power set of A is the set of all subsets of A, whereas 2 to the power of A is the set of all functions from A to a two element set 0, 1. These two are strictly speaking different, but there is a 1-1 correspondence to them, and so some people even identify them, that is identifying a subset with its characteristic function and using the notation 2 to the power of A for the set of all subsets of A set. Strictly speaking, that is not correct, but many people do that with this identification. If A is empty, how many elements are there? 0 elements. Then how many subsets will be there in the power set of A? Empty set will be having only one subset. So the power set of A will contain only one element. That is 2 to the power of 0 is equal to 1. And how many characteristic functions, that is how many functions will be there from 5 to a 2 element set 0, 1? Only 1. So this is about finite sets. If A is infinite, what happens? There's a question we will take up later. How to compare the, what is the number of elements, how will you compare the number of elements of an infinite set and the number of elements of the power set of that. There's a Cantor's theorem which states that these two are not equal. That is, a power set of of any set contains more elements, that is is bigger than any set. Power set is bigger than any set. That is the contention of the Cantor's theorem. We will discuss that when we consider Cartel numbers. Also, note that we discussed a property that two finite sets are having the same number of elements if and only if there is a bijection between them. If A and B are two finite sets having the same number of elements, then there is a bijection between them. And if there is a bijection between two finite sets, then they will have the same number of elements. This is a very crucial concept, and this is the basis for the concept of cardinality, by which we try to estimate the number of elements of infinite sets. Okay? Thank you.